But here's where the real mystery begins. Once your stomach has finished demolishing that pill and turning it into a soup of dissolved molecules and microscopic particles, all that material has to find its way through a very specific gateway to continue the journey. Your stomach is essentially a holding tank with only one exit, and that gateway has its own set of rules about what gets to pass through and what gets left behind. Highway to the bloodstream. That gateway leads to your small intestine, where the real molecular selection process begins. Your small intestine isn't just some passive tube that lets everything through. It's actually one of the most selective balancers in your entire body, and it has very specific rules about what gets to pass and what gets rejected. The wall of your small intestine is covered in these tiny finger-like projections called villi, and each villus is covered in even tinier projections called microvilli. All that surface area exists for one reason, to give your body maximum opportunity to absorb the stuff it needs while filtering out the stuff it doesn't want. But absorption isn't just about surface area. Your intestinal wall contains hundreds of different transport proteins, and these proteins are like highly specialized gatekeepers. Each type of transport protein only recognizes specific molecular shapes, kind of like locks that only work with certain keys. The 2025 research has identified over 400 different transport proteins in the human small intestine, and we're still discovering new ones. Some of these proteins actively grab onto drug molecules and pull them through the intestinal wall, while others act as barriers to keep certain molecules out. What makes this even more interesting is that different painkillers use completely different strategies to get through this intestinal security system. Ibuprofen molecules are just the right size and shape to slip through passive diffusion pathways, meaning they don't need any special transport proteins to help them. They just squeeze through tiny gaps between cells like molecular ninjas. But other painkillers need active transport, where specific proteins have to physically carry them across the intestinal barrier. The selectivity process is brutal. Studies from 2025 show that only about 60 to 80% of dissolved painkiller molecules actually make it through the intestinal wall. The rest get either broken down by intestinal enzymes or swept away by the constant flow of digestive juices moving through your gut. It's like a molecular obstacle course where most participants get eliminated before they even reach the finish line. Once those lucky molecules do make it through the intestinal wall, they don't go directly into your general bloodstream. Instead, they get collected by a specialized blood vessel system called the portal circulation. This is basically a private highway that carries everything absorbed from your intestines directly to your liver before it goes anywhere else in your body. Your liver gets first dibs on everything you absorb, which sounds helpful until you realize that your liver's job is to break down and eliminate foreign substances. Your liver contains the highest concentration of drug-metabolizing enzymes in your entire body. These enzymes have names like cytochrome P450, and they're essentially molecular shredding machines designed to tear apart foreign chemicals. When painkiller molecules arrive at your liver, they face what's called first-pass metabolism. This is where your liver immediately starts breaking down a portion of the drug before it ever gets a chance to reach the rest of your body. The numbers on first-pass metabolism vary dramatically between different painkillers. For some drugs, your liver destroys up to 70% of the absorbed medication during this first encounter. But ibuprofen is actually pretty good at surviving this process, maintaining about 95% bioavailability. That means if 100 milligrams of ibuprofen made it through your intestinal wall, about 95 milligrams will survive the liver's initial screening process. This is why pharmaceutical companies have to account for liver metabolism when they design pill dosages. They're not just calculating how much drug you need for pain relief. They're calculating how much you need to compensate for what your liver is going to eliminate. But your liver isn't just randomly destroying painkiller molecules. It's actually performing quality control. The liver breaks down drugs in the metabolites, and some of these metabolites are actually more active than the original drug. Other metabolites are designed to be easily eliminated by your kidneys. Your liver is basically a chemical processing plant that converts the raw materials from your pill into the specific molecular products your body can safely handle and effectively eliminate. After surviving the liver screening process, whatever remains of your dissolved painkiller finally enters what's called systemic circulation. This is the main highway system of your bloodstream that connects to every organ and tissue in your body. Your heart pumps about 5 liters of blood through this system every minute, creating a circulation loop that can carry molecules throughout your entire body. But even reaching systemic circulation doesn't guarantee success. Your bloodstream contains proteins that can bind to drug molecules and essentially put them in temporary storage. A significant portion of painkiller molecules in your blood are bound to these proteins at any given time, which means they're circulating through your body, but they're not actually available to do anything useful. Only the unbound molecules can exit your bloodstream and interact with tissues where pain is actually happening. The whole process from intestinal absorption to systemic circulation takes about 30 to 45 minutes for most modern painkillers. That timing has improved significantly since 2025 because of better understanding of transport proteins and metabolic pathways. Pharmaceutical companies now design pills specifically to optimize each step of this journey, from intestinal absorption rates to liver metabolism patterns. What's really mind-blowing is that this entire absorption and distribution system happens automatically every time you swallow any pill. Your body doesn't know whether you're taking a painkiller, a vitamin, or a completely inert sugar pill. It just follows the same molecular highway system regardless of what you've consumed. The selectivity happens at the molecular level based on chemical properties, not based on what you intended the pill to accomplish. Your bloodstream has become a molecular highway system with multiple lanes, checkpoints, and quality control stations. The molecules that do make it through this gauntlet are now circulating throughout your entire body. But here's where something really strange starts to happen. The everywhere problem. Your bloodstream is now carrying these molecules to literally every single part of your body. Your toes, your earlobes, your kidneys, your brain, everywhere. But wait, if I smash my thumb with a hammer, why is the painkiller going to my spleen? This seems like the most inefficient delivery system ever invented. This is the part that makes painkillers seem like magic because logically it makes no sense. You take one pill for a headache, and that same pill is simultaneously visiting your liver, your muscles, your bones, and about 37 trillion other cells that have absolutely nothing to do with your headache. It's like calling for pizza delivery and having the delivery guy stop at every single house in your neighborhood before finally reaching yours. But your cardiovascular system doesn't have any kind of GPS functionality. Blood just flows where blood flows, following the same circulatory routes it always follows, regardless of where you happen to be experiencing pain. Your heart doesn't pump harder toward injured areas, and your blood vessels don't create special express lanes for painkiller molecules heading to specific destinations. Once in your blood, the drug travels everywhere equally, reaching both injury sites and non-injured tissues. This systemic distribution is actually more sophisticated than it seems. What determines where these molecules end up first isn't your pain location, it's your blood flow patterns. Organs with the highest blood flow get the highest concentrations of painkiller molecules the fastest. Your brain, heart, liver, and kidneys see peak drug concentrations within the first 30 minutes simply because they receive the most blood per minute. Meanwhile, tissues with lower blood flow like cartilage, tendons, and bone take hours to reach peak drug concentrations. This creates a really interesting paradox. The places where you most commonly experience pain, like joints and muscles, are often the places that receive painkiller molecules last and in the lowest concentrations. Your knee cartilage has relatively poor blood supply, so it might take 2 to 3 hours for painkiller concentrations to peak there. But your brain, which processes the pain signals from your knee, gets flooded with painkiller molecules within the first few minutes. The tissue concentration data from 2025 studies reveal some surprising numbers. In highly vascularized organs, painkiller concentrations can reach 10 to 15 times higher than the average blood concentration. But in poorly vascularized tissues, concentrations might only reach 10 to 20% of blood levels. So the drug isn't distributed evenly throughout your body at all. It's more like a flood that hits some areas with tsunami-level concentrations while barely trickling into others. But here's the thing that makes this seemingly wasteful system actually brilliant. Different tissues have different barriers to drug penetration, and the everywhere approach compensates for these barriers by providing multiple pathways for the drug to reach its targets. Your blood-brain barrier normally keeps most chemicals out of your brain, but the everywhere approach means painkiller molecules are constantly encountering this barrier from multiple directions, and eventually some of them get through. What's really fascinating is that the everywhere distribution isn't actually wasteful at all when you understand what's happening at the molecular level. Pain isn't just happening at the injury site. It's happening throughout your entire nervous system, from the peripheral nerves at the injury location all the way up to the pain processing centers in your brain. The everywhere approach ensures that painkiller molecules are available to interrupt pain signals at every point along this pathway. The mechanism behind pain relief isn't about the painkiller finding your injury and fixing it. It's about the painkiller being available wherever pain signals are being generated, transmitted, or processed. Pain signals travel through peripheral nerves, up your spinal cord, and into multiple brain regions. The everywhere approach stations painkiller molecules at every stop along this journey, ready to interfere with pain signal transmission wherever it's happening. Recent 2025 data on pain pathway research shows that effective pain relief requires drug action at multiple sites simultaneously. Blocking pain signals at just the injury site provides minimal relief because the pain amplification happens throughout the nervous system. But having painkiller molecules distributed everywhere means they can block pain signals in peripheral nerves, spinal cord relay stations, and brain processing centers all at the same time. This creates a compound effect where the pain relief is much greater than what you'd get from targeting any single location. It's like having a security system with cameras and alarms at every possible entry point instead of just monitoring the front door. Most attempts to break in get stopped at multiple checkpoints, making the overall system much more effective than any single point of protection. The distribution kinetics also work in your favor, in ways that aren't immediately obvious. As painkiller molecules get metabolized and eliminated from highly vascularized organs, the drug concentrations in poorly vascularized tissues are still building up. This creates a sustained release effect where pain relief continues even as blood drug levels are declining. Your circulatory system essentially becomes a molecular distribution network with millions of delivery points operating simultaneously. Each blood vessel, each capillary bed, each tissue interface becomes a potential site where only free drug molecules can leave blood vessels and reach tissue receptors. The everywhere approach turns your entire cardiovascular system into a massive parallel processing pain relief operation. The sophistication of this system becomes obvious when you realize that it works for different types of pain simultaneously without any additional coordination required. Whether you have a headache, a sore muscle, and a small cut all at the same time, the same painkiller molecules distributed throughout your body can address all three pain sources concurrently. No targeting required, no coordination needed, just millions of molecular repair crews deployed everywhere and ready to work wherever they encounter pain signals. But there's something about this whole process that doesn't quite add up. If painkillers are flooding your entire body, why do you only feel relief in the places that actually hurt? Pain's secret identity crisis. The answer lies in understanding what pain actually is and where it really happens. You stub your toe and feel pain in your toe, right? Not exactly. Pain signals originate in injured tissue, but the conscious experience is created in brain circuits about 3 feet away from where you think it's happening. Your toe sends the distress signal, but your brain writes the pain story. This completely flips everything we think we know about pain on its head. When you touch a hot stove, the burning sensation feels like it's happening right there on your fingertip.
But that's just your brain's incredibly sophisticated
interpretation system. The actual experience of burning is being constructed entirely within your cranium by electrical signals and chemical reactions that translate tissue damage into conscious suffering. The 2025 neuroscience research has confirmed what sounds like science fiction. Brain imaging studies using advanced fMRI technology can now watch pain being manufactured in real time inside people's heads. They can see the exact moment when electrical signals from an injury get interpreted into the conscious experience of hurt. The brain regions that light up during pain processing are completely separate from the body part that's actually damaged. Scientists can literally watch your brain interpret incoming signals as pain. When researchers showed people virtual nature scenes while they were experiencing controlled pain stimuli, the brain scans revealed something incredible. The brain's interpretation of those pain signals was significantly reduced just by looking at pretty pictures. The injury was exactly the same, but the brain decided to process the incoming information differently. The pain processing pathway starts with specialized nerve cells called nociceptors that detect tissue damage and send electrical signals through your spinal cord to your brain. Your brain then constructs the pain experience using multiple regions, including the thalamus, somatosensory cortex for location and intensity, and emotional centers that make the experience unpleasant and motivating. But if you want to see just how much pain depends on brain interpretation, look at phantom limb pain. People who have had arms or legs amputated often continue to feel excruciating pain in body parts that literally don't exist anymore. The limb is gone, completely absent, but the brain keeps generating pain sensations and projecting them onto empty space. This shows the brain can generate pain without any actual injury present. Think about what this means. A person can have absolutely nothing wrong with their body, no tissue damage, no inflammation, no injury of any kind, and still experience pain so severe it interferes with their daily life. The pain is completely real from their perspective, but it's being generated entirely by brain circuits that are essentially creating the experience from memory patterns. Your brain constructs the experience of pain from electrical signals the same way it constructs the experience of vision from light waves, or the experience of hearing from sound waves. Pain isn't something that gets transmitted from your body to your brain like a package being delivered. It's something that gets created by your brain using information from your body. The difference is huge. The 2025 understanding of pain processing shows just how complex this construction process really is. When you get injured, the electrical signals travel through multiple relay stations and get distributed to different brain regions that each contribute specific aspects to the final pain experience. The somatosensory cortex handles location and intensity information. The anterior cingulate cortex adds the emotional component, making the pain feel unpleasant and motivating you to do something about it. The insular cortex integrates everything into a unified conscious experience. But here's where evolution shows its twisted logic. Why would natural selection design a system where pain gets processed in your head instead of at the actual injury site? It seems incredibly inefficient to have all pain signals travel all the way to your brain just to get interpreted and then have response signals travel all the way back to coordinate a reaction. The answer is that centralized pain processing gives your brain incredible power to modify and control the pain experience based on context. If pain happened locally at injury sites, it would be the same intensity every time regardless of the situation. But centralized processing allows your brain to turn pain up or down depending on what's happening around you. Soldiers in combat often don't feel injuries until after the fighting stops because their brains are suppressing pain signal interpretation to keep them functional. Your brain can also amplify pain when it decides that's necessary. The 2025 data on chronic pain conditions shows that about 50 million adults in the United States experience chronic pain, and most of these conditions involve the brain amplifying pain signals far beyond what's actually happening in the tissues. Conditions like fibromyalgia produce widespread pain even though there's no detectable tissue damage anywhere in the body. The brain regions that process pain also connect directly to memory centers, which is why painful experiences get remembered so vividly. But this also means that remembering pain can actually recreate aspects of the pain experience. People with chronic pain often develop something called central sensitization, where their pain processing circuits become hyperactive and start generating pain responses to normal, non-painful stimuli. Recent discoveries about pain processing show that the brain doesn't just passively receive pain signals, it actively participates in creating them. Brain regions like the periaqueductal gray send signals back down to the spinal cord that can either enhance or suppress incoming pain signals before they even reach conscious awareness. Your brain is constantly adjusting the volume knob on pain interpretation. The genetic research from 2025 has identified specific genes that control pain sensitivity by affecting how these brain circuits function. Mutations in genes like SCN9A can make people completely unable to feel pain or can make normal touch feel like burning agony. The same genetic variation that makes one person barely notice a paper cut can make another person experience that same paper cut as excruciating torture. This brain-based interpretation system is exactly what makes painkillers possible in the first place. If pain really happened at injury sites, you'd need to deliver painkillers directly to each injured tissue. But since pain actually gets constructed in your brain, you can interrupt the entire pain experience by getting painkillers to the right brain circuits. Your brain is essentially interpreting electrical signals and turning them into the conscious experience of pain. But here's what's really interesting. If your brain is constructing pain from incoming signals, what exactly are those signals trying to tell your brain in the first place? There's a whole molecular drama happening at injury sites that's specifically designed